NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams.
In a new world-shattering revelation, the James Webb Telescope has delivered the unthinkable: evidence of life on Proxima b, an exoplanet orbiting the closest star to the Sun. This discovery is nothing short of groundbreaking, representing humanity's first confirmation of life beyond Earth. What began as a promising observation of this rocky world has transformed into one of the most profound revelations in human history, a discovery that will undoubtedly alter our understanding of life's potential across the cosmos. Join us in today's episode as we dig deep into the latest stunning observations of Proxima b and how it could change everything we know about the universe. As shocking as it sounds, we find exoplanets, or planets orbiting stars other than our Sun, all the time now. We know of nearly 6,000 such planets plus another 10,000 planet candidates. So what makes Proxima b so particularly exciting? First off, Proxima b is roughly 4.2 light-years away, orbiting its red dwarf host star Proxima Centauri, the closest star to the Sun. This close proximity allows astronomers to study it in ways that are simply impossible with more distant exoplanets. Its mass is nearly identical to Earth's, at about 1.17 times that of our planet, and its size is also comparable. Proxima b completes an orbit around its star in a mere 11.2 days, remarkably fast compared to Earth's 365-day orbit. But since Proxima Centauri is a red dwarf, it's a much smaller and cooler star than our Sun. This means that even though Proxima b is incredibly close to its star, it still falls within Proxima Centauri's habitable zone, a range where conditions might be just right for liquid water to exist. This delicate balance of distance and temperature could, in theory, allow Proxima Centauri b to have water on its surface, a fundamental ingredient for life as we know it. The planet receives a similar amount of solar energy from its star as Earth does from the Sun, further supporting the possibility of a temperate environment. However, while this arrangement sounds ideal, several factors must be considered before we can truly assess Proxima b's habitability. Habitability on any planet depends on an interplay of various factors, including surface temperature, atmospheric composition, water availability, and the levels of radiation from its star. One of the most significant challenges Proxima Centauri b faces is the environment created by its red dwarf star. Red dwarfs are notorious for emitting intense stellar flares, bursts of energy and radiation that can bathe nearby planets in harmful radiation. These flares could strip away Proxima b's atmosphere over time, especially if the planet lacks a strong magnetic field to shield itself. For Proxima Centauri b, radiation levels may be quite different from those on Earth, adding complexity to the question of habitability. What further complicates matters is that the usual methods we rely on to detect biosignatures, or signs of life, don't work well with Proxima Centauri b. Most exoplanets are discovered using the transit method. This method involves observing a planet as it passes directly in front of its star from our perspective, causing a temporary dip in the star's brightness. These transit events also allow astronomers to analyze the star's light as it filters through the planet's atmosphere, revealing the presence of certain molecules. By studying the wavelengths of light that get absorbed as the planet transits, scientists can identify various gases, such as water vapor, carbon dioxide, or methane, that may hint at life. However, Proxima Centauri b doesn't transit its star from our vantage point, so we can't directly study its atmosphere this way. Instead, Proxima Centauri b was discovered using a different approach known as Doppler spectroscopy, or the wobble method. This method detects slight shifts in the star's spectrum as it moves towards and away from Earth, influenced by the gravitational tug of Proxima Centauri b as it orbits. Through Doppler spectroscopy, we can deduce details like the planet's mass and orbital period, but without transits, analyzing its atmosphere remains challenging. Despite these hurdles, astronomers are exploring alternative methods that may allow us to detect signs of life on Proxima Centauri b. One intriguing possibility lies in observing artificial light on the planet's night side. Imagine looking at Earth from a distant vantage point in space. The most conspicuous indicator of life on the planet at night would be the glow of artificial lights from cities. In principle, if a civilization on Proxima Centauri b were using artificial illumination, we might be able to detect it by analyzing the reflected light from its night side. For example, the kind of artificial light used by human civilizations, such as LEDs, has a specific spectrum. Theoretically, similar illumination from Proxima Centauri b could appear in telescope observations as an unusual reflection pattern, distinguishable from natural light sources. While challenging, this method has been used in our own solar system to observe planets that don't transit the sun. By analyzing the reflective light of these worlds, we can infer surface features and, potentially, even detect artificial illumination. Detecting the reflected light from Proxima Centauri b would be a remarkable achievement. Given that this light would be minuscule compared to the brightness of its star, it's akin to spotting a firefly near a searchlight. However, advancements in telescope technology have opened up possibilities that were unimaginable even a decade ago. The James Webb Space Telescope, along with its highly sensitive infrared detectors, is well suited to observe faint reflections from exoplanets like Proxima Centauri b. Webb's capabilities are revolutionary. The telescope's large, precision-crafted mirrors gather and focus light from distant objects, channeling it through various filters and spectroscopic tools to detect faint infrared signals. These innovations enable James Webb to capture data from far-off planets and stars with unprecedented accuracy. As such, the telescope could potentially pick up on dim, artificial illumination on Proxima Centauri b's night side. Astronomers have modeled artificial illumination as a percentage of the solar illumination reflecting from the planet's day side, with 0% indicating no artificial light and 100% suggesting a brightness equal to daylight. If Proxima Centauri b's night-side illumination reached just 5% of its day-side brightness, the James Webb could detect this with about 85% certainty, and at 9%, the detection confidence would rise to 95%. In recent observations, the Webb telescope has directed its powerful sensors toward Proxima Centauri b, yielding data that scientists are eager to analyze. Initial findings indicated that the planet's atmosphere contained a curious mix of gases that are strongly associated with biological processes on Earth. Spectroscopic analysis revealed not only the presence of water vapor, which suggests that liquid water may exist on the planet's surface, but also an intriguing balance of oxygen, carbon dioxide, and methane. This combination of gases is what scientists refer to as a biosignature, an atmospheric signature that strongly suggests biological activity. Methane, in particular, is a key indicator because it breaks down quickly in the presence of oxygen, meaning that something must be replenishing it. On Earth, this replenishment is primarily done by living organisms, especially microorganisms. While methane can be produced by volcanic activity or chemical reactions, the ratios of gases on Proxima b are far more consistent with biological processes than with abiotic ones. James Webb's instruments were able to detect a steady, ongoing production of methane and oxygen, which points to the existence of a stable ecosystem. In addition, trace amounts of nitrous oxide, a gas often produced by bacteria on Earth, were also found, adding further weight to the hypothesis that life exists on the planet. While atmospheric biosignatures provide compelling evidence, the observations made by James Webb have gone further, hinting at the possibility of a surface teeming with life. Through the telescope's highly sensitive infrared imaging, scientists were able to construct a detailed picture of the planet's surface conditions. What they found was astounding. Proxima b appears to have large areas covered in what could be liquid water, seas, or oceans. Alongside these bodies of water, James Webb has captured what scientists believe are signs of organic pigments, possibly similar to chlorophyll on Earth, which plants use to photosynthesize. These pigments could indicate that simple plant-like organisms are thriving on Proxima b, using the dim light from Proxima Centauri to produce energy. Furthermore, Webb's thermal imaging data suggests that Proxima b experiences significant temperature variations between its day and night sides, as one side of the planet is tidally locked to its star. Despite these harsh conditions, the presence of liquid water and possible photosynthetic life forms suggests that life has adapted to survive in these extremes, much like extremophils do in Earth's most hostile environments. Some researchers have even speculated that more complex life forms could exist on Proxima b. Although no direct evidence of such creatures has been found, the possibility cannot be ruled out. The presence of organic pigments and methane-producing microorganisms could point to a diverse biosphere, where a range of life forms have evolved to occupy different ecological niches. After all, the discovery of sign of life on Proxima b raises profound questions about the origin of life itself. Did life arise independently on this distant world, or was it seeded through a process like panspermia, where life's building blocks are spread throughout the galaxy by comets or meteorites? The answers to these questions could reshape our understanding of biology and the prevalence of life in the universe. Either ways, Proxima Centauri is a red dwarf star, much cooler and dimmer than our Sun. These types of stars are known for their violent stellar flares, which can strip away a planet's atmosphere and make the surface inhospitable. However, Proxima b has somehow retained an atmosphere, suggesting that it may have a strong magnetic field or other protective mechanisms that shield its surface from harmful radiation. The conditions on Proxima b may mirror those of early Earth, where life arose in oceans rich with organic molecules and energy sources like volcanic vents. It's possible that life on Proxima b followed a similar path, developing in water-rich environments where chemical reactions fueled the emergence of simple organisms. The discovery of biological gases like methane and nitrous oxide suggests that microbial life has adapted to Proxima b's unique conditions, possibly leading to a stable ecosystem. If life on Proxima b did indeed arise independently, it would suggest that the universe is teeming with life. Perhaps even that life is a natural outcome when the right conditions are present. Alternatively, if panspermia played a role, it would imply that life's seeds can travel vast distances across space, potentially making life on Earth and Proxima b distant relatives. And of course, such a discovery is more than just a scientific milestone. It is a turning point in human history. For centuries, we have gazed at the stars and wondered if we were alone in the universe. This question has haunted human imagination for thousands of years. Ancient civilizations held beliefs about the stars that were deeply intertwined with their cultures and religions. For the ancient Greeks, the night sky was filled with gods and heroes. Stars and constellations represented mythological figures, and their movements were believed to influence human fate. The philosopher Democritus, one of the first to theorize about the existence of other worlds, suggested that there could be countless stars, some with their own planets and even the potential for other beings. His ideas were radical, and they laid a foundation for considering the possibility of life beyond Earth. In India, the Vedas, a collection of ancient texts, imagined the universe as cyclically created and destroyed by divine forces, spanning immeasurable scales of space and time. Similarly, in Mesoamerican cultures, the cosmos was often represented as a multi-layered world connected by gods and spirits, with the stars serving as the heavenly realm of the ancestors. Ancient Chinese astronomers meticulously observed celestial phenomena, interpreting them as signs that could influence earthly affairs, but also pondering the nature of the stars themselves. Such beliefs reflected an early recognition that the universe is far vaster than what meets the eye, fostering curiosity about other worlds. Across these cultures, however, the question of life beyond Earth lingered, impossible to answer with certainty, but captivating enough to persist. During the Renaissance, revolutionary thinkers like Nicholas Copernicus and Galileo Galilei changed humanity's understanding of the cosmos. Copernicus's heliocentric model, which proposed that the Earth orbited the Sun rather than the other way around, shifted our perspective on our place in the universe. Galileo's telescopic observations revealed that the Moon was not a perfect, ethereal body, but a rocky landscape, much like Earth. Suddenly, celestial bodies were no longer seen as divine realms, but as physical worlds that could, theoretically, host life. This shift in thinking opened the door to a new wave of speculation. Giordano Bruno, an Italian philosopher, was one of the earliest to propose the idea that other stars might have their own planets, which he believed could host other forms of life. Bruno's ideas were so radical for the time that he was executed by the Inquisition, but his writings would inspire future generations of scientists to consider the possibility of a universe teeming with life. The advances of the Renaissance laid the groundwork for modern science, shifting from a worldview in which humanity was the center of creation to one where Earth was merely one planet among many. As telescopes improved, astronomers like Johannes Kepler and Isaac Newton contributed to the understanding that the laws of nature were universal. The realization that other stars operated under the same principles as our own sun was a profound one, suggesting that other planets and possibly life could exist under similar conditions. By the time of the scientific revolution in the 17th and 18th centuries, curiosity about life on other planets had developed from a speculative philosophy into a scientific question. As telescopes became more powerful, astronomers observed features on planets like Mars that seemed to suggest geological activity and even seasonal changes. The Martian canals, popularized in the 19th century by astronomer Giovanni Schiaparelli and later by Percival Lowell, fueled public imagination about the possibility of intelligent Martians constructing vast networks of waterways. These observations sparked a wave of Mars mania, and works like H.G. Wells' The War of the Worlds reflected a popular fascination and fear of alien life. In scientific circles, however, the question of extraterrestrial life remained unanswered. Despite increased understanding of our neighboring planets, the evidence was insufficient to confirm or deny the presence of life. However, the scientific revolution ushered in an era of rigorous astronomical study. William Herschel, the discoverer of Uranus, believed that other planets, including Jupiter and Saturn, might be inhabited. This era of study set the stage for the 20th century, where rapid technological advancements would bring humanity closer to understanding our place in the universe. The launch of Sputnik in 1957 and the subsequent space race marked a turning point in humanity's quest to explore the cosmos. By the 1960s, space exploration had moved beyond Earth's atmosphere, and scientists began to consider the practicalities of finding life beyond our planet. The search for extraterrestrial life shifted from speculation to targeted investigation, with NASA's Viking missions to Mars in the 1970s representing some of the first efforts to directly seek out biological evidence on another world. The 1977 launch of the Voyager probes pushed the boundaries of human exploration even further. Equipped with a golden record containing sounds and images from Earth, the Voyager missions were designed to reach the outer planets and beyond, carrying with them a message to any intelligent life they might encounter. The golden record remains humanity's first interstellar message, a hopeful gesture encapsulating our desire to connect with other beings. During the same period, the scientific community also began efforts to listen for alien signals through projects like SETI, or Search for Extraterrestrial Intelligence. Utilizing radio telescopes, scientists started monitoring the sky for signals that might indicate intelligent life. While no confirmed extraterrestrial signals have been detected, SETI has inspired a range of similar initiatives, leading to an ongoing worldwide effort to scan the cosmos for signs of intelligent communication. In 1995, astronomers discovered the first exoplanet orbiting a sun-like star, 51 Pegasi b, marking a watershed moment in the search for extraterrestrial life. Since then, the discovery of thousands of exoplanets has completely transformed our understanding of the universe. With missions like Kepler, TESS, and most recently, the James Webb Space Telescope, scientists have found that planets are not rare, but incredibly common, with many potentially existing within their star's habitable zones. The future of the search for extraterrestrial life is as exciting as it is uncertain. The solar system has become the heart of this endeavor. Several celestial bodies in our own neighborhood emerge as prime candidates, with Mars, Europa, Enceladus, and Titan leading the way. Mars has captivated the imagination of scientists and the public alike for centuries. This planet has the most Earth-like environment of any in our solar system, which is why it has long been a focus of astrobiological research. Historically, Mars was likely very different from the cold, barren landscape we see today. Geological evidence points to a Mars with rivers, lakes, and perhaps even a vast northern ocean. Although current conditions on Mars are harsh, with a thin atmosphere that cannot retain much heat and high levels of surface radiation, scientists believe there may still be microbial life hiding in more protected environments. Beneath Mars's surface, microbial life might have found a haven in aquifers, regions of rock and soil that hold liquid water. Such subsurface locations offer a potential sanctuary, shielded from the planet's thin atmosphere and solar radiation. These environments may contain conditions conducive to microbial life, with water and possibly other organic compounds that microorganisms would need to survive. The significance of Mars as a potential habitat for life has led to ambitious exploration efforts. Future missions will continue to target Mars in hopes of confirming its habitability. The upcoming Mars Sample Return mission is a collaborative effort between NASA and the ESA that aims to retrieve samples from Mars's surface and bring them back to Earth. By carefully examining these samples, scientists hope to uncover organic molecules or even fossilized microbes, which would be groundbreaking evidence that Mars once supported, or may still support, life. If successful, this mission could fundamentally reshape our understanding of life's prevalence in the universe, with Mars standing as a tantalizing reminder that life might be closer than we ever imagined. Jupiter's icy moon. Europa presents another compelling target for astrobiologists. With an ice-covered surface hiding a vast ocean beneath, Europa holds one of the most promising environments for life in our solar system. Its subsurface ocean, warmed by tidal forces generated by Jupiter's gravity, is thought to have existed for billions of years. This prolonged stability creates an environment where life could theoretically evolve and flourish, shielded from the deadly effects of solar radiation. Europa's subsurface ocean is especially intriguing because it is likely salty, similar to Earth's own oceans, and it may even interact with the rocky seafloor. This interaction could potentially generate hydrothermal vents, which are known to support life on Earth's ocean floor. These underwater environments on Earth are home to ecosystems teeming with unique organisms that thrive without sunlight, using chemical reactions instead of photosynthesis for energy. The possibility of similar vent systems on Europa's seafloor has led scientists to believe that microbial or even complex life could exist in its depths. To explore this icy moon, NASA's Europa Clipper mission, scheduled for launch in the 2020s, will conduct an unprecedented examination of Europa's ice shell and subsurface ocean. By flying multiple times over Europa's surface, the Clipper will search for evidence of life by analyzing the chemical composition of the moon's icy crust and scanning for potential thermal anomalies that could indicate active processes below the ice. Clipper's instruments will also analyze Europa's thin atmosphere for molecules that could be biosignatures. If life is present, or if there are even conditions that resemble a habitable environment, Europa Clipper may well find them. Saturn's moon Enceladus is perhaps one of the most intriguing candidates in the solar system for finding life. Like Europa, Enceladus has a subsurface ocean beneath an icy crust, but what sets it apart are its spectacular geysers. These geysers shoot plumes of water vapor, ice particles, and organic compounds from the moon's interior directly into space, offering a direct glimpse into Enceladus's inner ocean. This phenomenon provides scientists with an extraordinary opportunity to study the ocean's composition without having to drill through the ice. NASA's Cassini spacecraft made flybys of Enceladus in the early 2000s and analyzed the composition of these plumes, detecting organic molecules such as methane. This discovery was remarkable because methane is often associated with biological processes on Earth. While methane can also be produced by non-biological processes, its presence on Enceladus has encouraged astrobiologists to consider that the moon's ocean might host microbial life, or at the very least, conditions conducive to life. Due to these findings, there are now numerous proposals for follow-up missions to Enceladus, each aiming to study its plumes in greater detail. These missions are in various stages of planning, with many scientists advocating for a dedicated life detection mission to explore the plumes more closely. A spacecraft could fly through the plumes, capturing samples and analyzing them for complex organic molecules or even potential biosignatures. With each discovery, Enceladus brings us closer to answering the age-old question of whether life exists beyond Earth. Another fascinating location in the search for life is Saturn's largest moon, Titan. Unlike any other body in our solar system, Titan has a dense atmosphere and surface lakes of liquid methane and ethane. Titan's environment is vastly different from Earth's, with temperatures so cold that water exists as solid ice. However, scientists speculate that life might be able to emerge and thrive in Titan's hydrocarbon lakes, where methane serves as the primary solvent rather than water. Methane-based life, if it exists, would be unlike anything we know on Earth, challenging our assumptions about life's chemistry and what constitutes a habitable environment. On Earth, life is carbon-based and relies on water as a solvent, but Titan presents a unique opportunity to explore the possibility of a different kind of biochemistry. Some scientists believe that organisms on Titan, if they exist, might metabolize hydrogen and acetylene and excrete methane, a reverse of the process seen on Earth. NASA's Dragonfly mission is set to revolutionize our understanding of Titan. Scheduled for the mid-2030s, this rotorcraft mission will explore Titan's dense atmosphere and surface, conducting experiments to analyze the moon's organic molecules and atmospheric composition. Dragonfly will investigate whether the complex chemistry on Titan's surface and in its atmosphere is conducive to life, potentially expanding the definition of what we consider a habitable environment. In addition, as told in recent years, the discovery of thousands of exoplanets, planets orbiting stars outside our solar system, has transformed the search for life. Advanced telescopes and observatories are enabling scientists to study these distant worlds in unprecedented detail. The historical launch of James Webb marked a significant leap in the search for life. Its powerful infrared capabilities allow it to study the atmospheres of exoplanets, searching for signs of habitability or even biosignatures. Biosignatures are molecules or patterns in a planet's atmosphere that could indicate biological processes such as oxygen, methane, and water vapor. Webb is currently focusing on planets in the habitable zones of their stars, where conditions may allow for liquid water. Early observations have already yielded promising data, and as James Webb continues its mission, it may identify planets with atmospheres resembling Earth's, where life could potentially exist. And beyond James Webb, new observatories are in development that will enhance our ability to study exoplanets. The extremely large telescope, currently under construction in Chile, will be able to directly image some exoplanets and analyze their atmospheres. NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will conduct a survey of exoplanetary systems and search for free-floating planets, expanding our understanding of planet formation and habitability. Moreover, recent discoveries have widened the scope of potential biosignatures, encouraging scientists to consider not only Earth-like molecules, but also exotic chemistries that could indicate life. For example, on planets with a different atmospheric composition, unique combinations of gases, such as methane and carbon dioxide, could suggest biological processes. With an expanding list of potential biosignatures, future telescopes will search for multiple gases and their interactions, aiming to detect patterns that suggest biological activity rather than abiotic processes. While finding microbial life or simple organisms would be groundbreaking, detecting signs of advanced extraterrestrial civilizations or technosignatures would arguably be one of the most profound discoveries in history. Technosignatures are indicators of advanced technology that could suggest the presence of intelligent beings. The CD Institute has been searching for signals from intelligent civilizations for decades, primarily focusing on radio waves. Advances in technology are allowing scientists to broaden their search, incorporating optical signals and even bursts of laser light that could be sent as signals from a distant civilization. In recent years, breakthroughs in machine learning have also enhanced SETI's capabilities, enabling computers to analyze massive amounts of data quickly and detect potential signals that might have been missed by human observers. Besides, a Dyson sphere, a hypothetical structure that could capture a star's energy output, is a popular concept among scientists searching for technosignatures. Although no Dyson spheres have been found, astronomers continue to search for unusual patterns of dimming and brightening in stars that could indicate the presence of such megastructures. Telescopes capable of capturing infrared radiation are particularly valuable in this search, as a Dyson sphere would likely emit excess infrared light. Another technosignature that scientists consider is artificial pollutants. If a planet had significant levels of industrial gases like chlorofluorocarbons in its atmosphere, it might indicate technological activity. Additionally, scientists are exploring the idea of detecting city lights or other artificial illumination on distant planets. With future telescopes such as LIVOIR, also known as Large UV Optical Infrared Surveyor, it might be possible to detect these faint but potentially telling indicators. Last, note that the search for extraterrestrial life is about more than just finding new forms of biology. It's also a profound philosophical endeavor. If we were to discover even microbial life beyond Earth, it would imply that life is not unique to our planet. This would suggest that the universe is filled with the potential for life, challenging many of humanity's long-held beliefs about our place in the cosmos. Furthermore, finding life on another planet would raise ethical questions. How would we treat alien life? Should we make contact if it were intelligent, or would we risk contaminating other ecosystems with our own presence? These are pressing questions, especially if intelligent life were discovered. This discovery would immediately give rise to the ethical considerations that have only been theoretical until now. If life on another planet exists, it would not be enough to marvel at the scientific wonder of it. We would need to consider how we treat these extraterrestrial beings, ensuring that any action taken preserves both their existence and the integrity of their ecosystem. The concept of contact brings with it concerns about contamination. Just as we worry about bringing invasive species into foreign ecosystems on Earth, our presence on a planet that hosts life could have unknown and potentially irreversible effects. We may be driven by a noble curiosity to study these life forms, but what if our attempts to learn result in harmful consequences? The need to approach alien life with respect, caution, and humility becomes paramount, as we have learned from our past mistakes on Earth when invasive species or human interference altered or destroyed native ecosystems. If intelligent extraterrestrial life were discovered, humanity would have to wrestle with its long-standing sense of superiority. For thousands of years, we have lived with the assumption that we are the only beings capable of thought, emotion, and self-awareness. Confronting intelligence from beyond our world would mean seeing ourselves as part of a larger, possibly more complex web of conscious beings in the universe. This discovery could change the way we view concepts of self-awareness, community, and culture, possibly leading to an exchange of knowledge that would deepen our understanding of consciousness itself. In short, whether we find a single-celled microbe or a highly advanced civilization, the sheer knowledge that we are not alone would reshape our understanding of humanity and our place in the universe. To know that life, in whatever form, has managed to take root elsewhere, would prompt us to see ourselves in a new light. Our definition of life would no longer be limited to Earth's unique conditions, opening up new realms of thought about the adaptability and resilience of life itself. It might challenge us to pursue our survival more diligently, knowing that life elsewhere has managed to endure. The implications could even inspire us to better care for our own planet, recognizing Earth as a rare and cherished environment that has nurtured us for millennia. In the end, the search for extraterrestrial life is not merely about finding biological evidence. It is a philosophical, ethical, and existential journey. Each question raised, whether about contamination, communication, or coexistence, serves as a reflection of our hopes, fears, and aspirations as a species. The quest drives us to look beyond our world and, in doing so, to consider who we are in relation to the vastness of the cosmos. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.